Welcome to the video for topic 2.2 in AP Pre-Calculus, change in linear and exponential functions. So we've been studying arithmetic sequences and geometric sequences and their connections to linear functions and exponential functions respectively. And so in this lesson, we just go a little bit further and make sure we know how to identify from numerical evidence whether or not a function might be linear or exponential. We're really practicing the linear aspect of this because we've done that before. And we're seeing for the first time in some, again, numerical evidence through tables and some application problems, seeing more of the geometric sequence and its patterns. So we learned that arithmetic sequences behave like linear functions and geometric sequences behave like exponentials. So some reminders about arithmetic sequences. We have a couple formulas, and we know those formulas really directly correlate to slope-intercept form and point-slope form. And when we identified rates of change this way in the past, if it was linear, we knew there was some common difference, D, because of the constant rate of change, meaning the output values changed at a constant rate over equal input intervals, or we saw that constant first difference in our output values again over equal input intervals. So similarly with geometric sequences, because they change proportionally, in our numerical evidence, we're going to look for a constant proportional change, or we're going to look for that R value that gets multiplied to our inputs to make the change, to our outputs to make the change over equal input length, equal length input intervals. Sorry, kind of tongue twisters there. So geometric sequences, those formulas, they correlate to exponential functions. So we see a times b to the x or a times r to the x. We're going to get used to seeing that notation more and more. So again, it's very important to recognize and understand the similarities and differences in linear and exponential functions. So just pretty much saying what I've said in the past here in just the last minute or so. Over equal length input values, if it's linear, we're seeing a constant rate of change, meaning something's being added or subtracted on those y or output values. Exponential functions, we are going to look for a constant proportional change over equal length input values, and we're looking for some sort of multiplication. So flipping over, let's try a couple of examples. We're giving some tabular evidence of some patterns. We need to determine if they are linear, exponential, or neither, and we're going to give reason for our answer. So the first thing I'm double checking as I look at example A is, are my x values, my inputs, increasing by the same amount? Looks like they are increasing at a constant rate, adding 3 each time. So I'm just kind of double checking that. So I know I'm going to be able to say over equal length input intervals. And so now we're looking for the change in the y's. I notice each time in my outputs, we are decreasing by 2. And so because it's connected to addition or subtraction, I know that this must be linear. My constant rate of change, we can see a decrease of 2 units each time. And actually my rate of change would be, think about your rise, you're going down 2 units for every 3 units, so our slope is really negative 2/3. But we know because this has constant first differences, this must be linear. And if I were to explain this using words, it might sound something like over equal length input intervals, the output values change at a constant rate. So what if we tried part B? So again, the first thing I'm looking for are my x's changing equal interval. They sure are. I'm just going to kind of put a check mark. So now I'm looking for, am I either adding or subtracting the same amount? Or I can quickly see, definitely not adding the same amount. At first I'm adding 1, then I'm adding 3, then I'm adding 5. So it's definitely doesn't have a constant rate of change, meaning it's not arithmetic, right? So then I'm switching to, am I multiplying? Well, first to get to 0 to 1, right, we're multiplying by, that's not possible, and then times 4, and then times who knows what, right? So this appears to be neither. The output values are not changing at a constant rate or a proportional rate. Example C, again, double checking, are my x's changing at the same interval up 2 units each time? Looks good. And so now how are my outputs changing? 1 times 2 is 2, 2 times 2 is 4, times 2 is 8, times 2 is 16. So this time it looks like there's a proportional change, right? It looks geometric. My output values are geometric. And so we know this then would be exponential. And we can justify or give reason and say over equal length input values, or excuse me, input intervals, the output values change proportionally. Last one might be a good one for you to try. My x's are definitely increasing by the same interval, 5 each time. So that means I can keep going. You know, unfortunate aspect, our notes here don't exactly show you how to deal with it if it's not. The input values aren't changing at the same interval, so that will be something we'll experience as we move forward. But I'm now moving on to my outputs since the inputs are looking good. I'm either subtracting 40 to get to 40, but then subtracting 40 again wouldn't work, so it's definitely not linear. Is there a difference proportional? Looks like it's getting cut in half each time. 80, 40, 20, 10, etc. So this looks like it's exponential. And we really get to give a same description. And I'm going to see if I can be sneaky and potentially copy and paste that with my app. So there you go. So last couple of examples just to give you somewhat of some application, essentially some word problems to work with. Example 2. A wild rumor is spreading that Mr. Passwater won 3rd place in the World's Strongest Man contest. The number of people that heard the rumor can be modeled by a geometric sequence. So I'm immediately thinking about all my g sub n's being our kth term times our common ratio to n minus k. I'm thinking about that formula. And I see 43 people heard the rumor on day 3. So I can say day 3 g sub 3 would be 43 people. Writing some units might be helpful. So the g sub n's represent the number of people, but the n's represent the day. And then 140 people heard the rumor on day 6, so we can say g sub 6 is 140. So we are going to substitute g sub 6 as our k. I'm sorry, typically we want the bigger one to be g sub n. So I'm going to substitute g sub n with our g sub 6 and 140, and our g sub k is going to be g sub 3. So if I substitute those values in, G sub n is 140, G sub k is 43. We do not know what r is. N is 6 and k is 3. And so now we're going to solve for r. Divide both sides by 43. R to the third should be 140 over 143. And so taking a root of this, and then this is where I would encourage you to go to a calculator to figure out what that number is, because it's pretty abstract right now, but just leave it. So we can say r in its exact form, no decimals needed, is the third root of 140 over 43. Okay, another way to write that, if you prefer, which could be helpful in a little bit, is our radicals can be written as fractional exponents. And so when we cube root something, that's the same as raising it to a power of 1/3. So because my formula uses exponents, right, I'm actually going to choose that exponent version of r to plug into my formula. So I can say any G sub n, going back to what we used 43 as our kth term. R, I'm going to plug in using the exponent version, 140 to the power of 1/3. That whole thing is our r, so a couple parentheses to hold it all. And then n minus 3. Okay, so again, if you're like, I don't like how that looks, and you would rather write it as the third root of 140 over 43, that's fine. Truly, if you'd rather go decimal approximation of what the cube root of 140 over 43 is, that's also fine. But keeping the exact form like this one is going to guarantee that you get all the rounding, important rounding aspects correct. You know, mathematics and true mathematics and pure mathematics, I would say, we never use decimals until we're done, until we report an answer, because the sooner we round in our problem and then we keep rounding and keep using it, right, we lose accuracy. So try to get in the habit of using exact form. So really, we're being asked, I didn't finish reading this, according to the model, how many people to the nearest whole number have heard the rumor by day 10? So this is telling us to find G sub 10. So we're going to go ahead and plug that in. Calculator handy. Again, I'm going to just make sure I have those two different versions on screen to help you of what our R value is. Okay, so if we go punch this into the calculator, we should get 675.576. The question asks us to go to the nearest whole number, so we will have to round this one up. And we can say on day 10, there should be about 676 people. Last example. Feel free to pause and try it on your own. It says a large theater has rows of seats where the number of seats in each row can be modeled by an arithmetic sequence. So right then and there, I'm seeing arithmetic sequence. And so I'm thinking about my formula. All a sub n's is going to be a sub k plus our common difference times n minus k. We are told the fifth row has 31 seats, so we can interpret that as a sub 5 will be 31. The 11th row has 49 seats, so a sub 11 is 49. And we want to figure out how many seats there's going to be in the 25th row. So our goal is to figure out what is a sub 25. So just like the last example, we are going to go to the larger value. That's going to be our a sub n. And so a sub 5 is going to, a sub 5 is going to be our a sub k. So let's go ahead and plug those things in and work to solve for our unknown. A sub n is 49. A sub k is 31. We do not know our common difference. N is 11. K is 5. So if we start solving, 11 minus 5 is 6, so 6 times d. Subtract 31 on both sides, and then solve for d. What are we going to get? 49, 9, 9, 18. And so d is 3. And so our a sub n's is going to be a sub k, 31, plus our common difference, 3, n minus 5 times. So using this to find the 25th row, plug in a 25 for n. So a sub 25, our 25th row is going to have 31 seats plus 3 times 20, or 60 seats. So 60 plus 31, it would have 91 seats. That is it for topic 2.2, just a little bit more application and use. Or really, I hope this lesson is really serving as sort of a summary and connection creator for what we've talked about so far with rates of change and using our geometric and arithmetic formulas. Thanks for watching.